Okay, all right, let's see. Have we already asked, like, what is your favorite candy? Have we already done this? There's a good chance we might have. No, we haven't. Okay, great. So then this is overdue from Halloween. So now we have a good excuse of using this. Okay, amazing. So go ahead and put in the chat, what is your favorite candy? And then I'll keep going ahead and checking out the rest of the messages. Okay, awesome. Amari, it's good to see you. Sai, it's good to see you too. Amari says, I told my math teacher, the main teacher in charge of math club about you, and he likes your work. Oh, that's so sweet. That's awesome, Amari. Thank you so much. That's really cool to hear. Oshrit says, hi. Hello, Oshrit. And hi, Jason. Okay, awesome. I'm starting to get some answers. So Tommy says, Twix, amazing. Twix is great. Now, the real question is left or right Twix. There is actually a difference. I learned that the other day. Let's see. Twix. Oh, I guess I should write like normally. Twix. Okay. Kit Kat from Psy. Awesome. Airheads. Cool. Tommy says left Twix. Okay. Um, there's like a difference. It's something about like the ratios and like the crunchy stuff and the caramel stuff. Let me see if I can find it. It's like I didn't know it was a thing until my friend told me. But I think there's actually a difference. No one can really tell though. Um, yeah, I think like the left Twix is more like it's more like crunchy, and the right Twix is more like caramelly, I think. I don't know. But I think that's like roughly what it is. Okay. M&Ms, awesome. I feel like okay, I don't know if I don't really like the normal M&Ms, but I like the peanut butter filled ones. Not the peanut ones, but the peanut butter filled ones. I think those are good. Um, what else is there? Amari says Skittles, peach rings. Oh, I love peach rings. Peach rings are great. Or lifesavers. Okay, so you're like totally a gummy person, Amari, which is okay. Me too. I'm low-key also a gummy person. Lifesavers. Although recently I feel like I've been getting back into chocolate. Like I like a lot of chocolate. Oshrit says Hershey's. Nerds, gummy clusters. Honestly, that's the only way to eat nerds. I feel like if you just have the normal nerds and not the gummy stuff, like that's hard to eat. Oreos. Ooh, I wouldn't know. I don't count Oreos as candy, but Oreos are good, so I'll put it on here. Oreos are pretty fire. Let's see. Kit Kat, Snickers. Oh yeah, Snickers are great. Sometimes I think Snickers have too many nuts and it takes away from the chocolate flavor, but they're okay. Every now and then they're okay. Milky Way, I love Milky Way. Because it's like Snickers with no nuts. So I'll take Milky Way any day. All right. Let's see what else we have. M&Ms and so on. Wow. Asha says, "Is there a mathematical way to show how many candies I like?" I actually, you know what? One day we could do like a graph kind of thing where we just like graph the candy that everyone likes. That would be really interesting to see. Tommy says Swedish fish. Ooh, I'm gonna have to really disagree with you on this. I do not like Swedish fish at all. I think they are the budget version of Sour Patch. But some people like Swedish fish, so that's my take. Kit Kat and M&Ms from Sumhith. I've never heard of this ghost toast thingy. That's interesting. Okay, cool. Dairy milk. Ooh. Oh, wait, like the chocolate. Yeah. Okay, yes. I agree with that. Yeah. The chocolate is super good. I don't like milk like by itself though, so I was like confused about it. But yeah, the dairy milk chocolate is good. Amazing. Takis are the best. Unfortunately, Takis are not candy, so I'm not gonna put that down. Bitwix, Almond Joy. Yeah, I think Almond Joy. I feel like Almond Joy gets so much hate, but I like Almond Joy. It's a nice coconut chocolate thingy. It's nice. Oh, hold on. Let me go ahead and stop sharing. I forgot to disable annotations. Okay, now we're good. All right. No drawing anymore. Cool. Yeah, I guess you can use sets, like maybe to show like how much everyone likes something. Maybe, yeah. I see Bobbits of Sour Patch and Warheads. Awesome. Oh, Smarties. Yeah, okay, this is like an old one. I feel like Smarties are just not that common anymore. I like Smarties. Oh, I love Almond Joy Summit. Oh my goodness. No, Almond Joy is good. I like coconut, so like that's why I like it. But I guess to each their own. Like you say you like Milk Duds. I do not like Milk Duds at all. But yes, I guess everyone has different tastes. Oh, Twizzlers. Yes. I do not like Twizzlers and Vika, but I'm glad that you take pride in your candy. I think that's awesome. Amari's, let's see, Asha says, how many candies did you all eat so far? And Amari says, my mom kept my Halloween candy because she did trust the people in the neighborhood. That's funny. Abik says Milky Way. Awesome. Jason says Starburst. Oh yeah, Starburst. I forgot about that. Almond Joy. Ooh, lollipops from Psy. Yeah, lollipops have so many variety. It's like a nice one. Um, okay, Summit says, I don't know how people eat Twizzlers, Airheads, or Jolly Ranchers. Okay, Airheads I could kind of get. Jolly Ranchers I don't get at all because it's very hard to eat. But yeah, jelly beans. Cool. Okay, wow, this is really great. My whole screen is filled up, which is good. This means we have a lot of variety and just all the candy that everyone loves, which is awesome. Which is awesome. Okay, amazing. So on that note, let's go ahead and kind of transition to the math bit. So if we want to start thinking about our concepts for today. So today's topic is actually like one of my favorite parts of number theory. So like I've already prefaced like I love number theory. It's my favorite subject in math. Today we are going to do a really, really exciting part of number theory. So this I'm like super excited to teach this. Today is about modular arithmetic. How many of you guys have heard of modular arithmetic? Okay, a couple. Awesome, awesome. But not everyone. Okay, this is interesting. This is cool. Yeah, so this is definitely like not taught in school. Like even in high school, this is not taught. Well, to be fair, I guess like a lot of number theory isn't taught, but modular arithmetic is like not really taught. Maybe if you take a CS class, it'll be taught. But it's not a difficult concept. It sounds good though. So modular arithmetic is basically this idea of working with remainders. And before we get in any deeper than that, let's kind of talk about like the motivation for this or like potentially some of the applications, right? So if you're like looking, okay, so in the US we use 12-hour time. But like elsewhere in the world, like there's 24-hour clocks, or that's military time for us. So like whereas we say 6 p.m., that'll be like that should be 18 o'clock somewhere else in the world. So in the other part of the world, like they don't say PM, they just say 18 o'clock, and they'll know automatically that it's going to be 6 p.m. So for us, we have to put this PM because if we just say 6 o'clock, well, that could be AM or it could be 6 p.m., right? So this kind of helps us distinguish between two times. But other people in the world will use like military time and say it's 1800. So they'll say it's 18 o'clock. Osher says my computer is a military time. Yeah. It can be easier for for some people. Yeah, it can absolutely be easier. You just have to do a little math to get the time, but yes. Okay, so this like idea of like military time to like the normal US time, this actually is like an example of modular arithmetic because what you're actually doing is you're wrapping around the hours, right? If you think about that like 12-hour clock, you have to go 12 hours first, and then to get to 6 p.m., you're going 12 hours, and then you got to go, you're wrapping around, and you're going an extra 6 hours to get to your actual time, right? Uh, and I guess like a better way to say this maybe is like let's say it's like 10 a.m., right? So you're here at 10 a.m. and you're gonna wait 5 hours. So let's say you do something for 5 hours and you check the clock. So after 5 hours, we can tell like obviously the time is gonna be 3 p.m., right? But like maybe if you have never worked with a clock before, I mean you guys have, but like pretend there's like an alien and they've never worked with a clock before and they say, oh, 10 a.m., 5 hours. It would seem like oh, this is 1500. hours, right? Like it's 1500 o'clock, but that's not true. Instead of saying 1500, we'll say it's 3 p.m. because we'll subtract that 12 and we'll kind of wrap around the clock. But this is like basic clockwork that you guys know. So this idea of like wrapping around the clock or like expressing it as like something that's less than 12 hours instead of greater than 12 hours here. That's going to be what we kind of call modular arithmetic. Okay, so we'll kind of say something like we can translate this into the expression 15 is congruent to 3 mod 12. Okay, so no questions. There is no problem yet. I'm kind of just motivating like what modular arithmetic is, right? So here's like the main idea we're going to be talking about. This is the main notation, okay? So let's break down a couple of things. First, this is like a number. This part doesn't matter. The more important part is this thing, okay? So this is congruent. This is basically saying like the two numbers on the side of our equation are the same. In normal equations, we have like equal signs, but in modular arithmetic, we have this congruent sign, which is like an equal sign, except it has an extra line, okay? And then this mod 12 stuff is like, what are we dividing by? So it's like, I guess it's the divisor. Yeah, that's like a good way to say it, divisor. And then this 3 is going to be like, kind of like, how do we make this equal to each other, right? So like, if you divide 3 by 12, you get a remainder of 3. If you divide 15 by 12, you'll also get a remainder of 3. So that's why we say like 15 is congruent to 3 mod 12, right? Because when you divide either of these numbers by 12, you'll get the same remainder both times, okay? So this mod is short for modulo, but no one ever says modulo, like everyone says mod. But yeah. Okay, awesome. So for those of you guys who have like never heard of modular arithmetic, is it clear? Okay, Bave says, I don't understand. All good, all good. So let's kind of talk about this a little bit more. Um, hmm. Okay, so let me get rid of this stuff. We'll return to this example. Okay, so let's say it's like 10 o'clock in the morning. At 10 o'clock, your clock will look a little something like, it says 12, 3, 6, or yeah, and 9. Okay, so your clock will look like something like this. This is probably like the hour hand. Okay, so this is like what your clock looks like. I guess like that. Okay, there you go. Okay, so this is like 10 o'clock. That's 10 a.m. Now, let's say you're looking at like 5 hours later, right? So you're gonna wait 5 hours, you're doing something, maybe you're doing some math problems, and after 5 hours, you check your clock again. And after 5 hours, notice like how on our clock face, there's the maximum number of hours we can have is 12. Like we can't go past 12, right? So when we do this, our clock hand is gonna move, it's gonna go up until 12, and then it's gonna start back again at 1. And then it's gonna go to 1, 2, and then finally to 3 o'clock. So 3 o'clock is gonna be like where our hand is now. So notice that like after 5 hours, our time is not like 1500, unless you're working in military time. But we're not working in military time. We're working in like normal time, the time you use on your in school or like in your like normal lives, right? So after like 10 a.m., we don't say, oh, it's 1500 o'clock. No, no, no. We say it's 3 p.m. And the reason why that is because when we're working with clocks, like the maximum number we can say is 12. So after 12, we just have to restart our clocks and add a PM at the end. So that's why like this will be like 3 p.m. and not 1500. We don't really say this, okay? So modular arithmetic, what it does is it kind of like looks at this idea of going around clocks, like wrapping around clocks. I think an easier way to understand this, like essentially is like, it's basically just representing division. Like this is the big idea. It's representing remainders in division, right? Because if you add 5 hours to 10, like yes, you'll get 15, but because you can't represent 15 in a 12-hour clock, you have to divide 15 by 12 and take that remainder of 3 hours, and that's going to be your new time, right? You're going to move that clock hand 3 extra hours. Okay, so this is like the essence of modular arithmetic, right? You're working with remainders in division. You're representing remainders. And this might seem like super niche, like why do we care about remainders? But it can actually come in handy a lot. There's a lot of cool questions that can be solved by this. Okay, so let me pause here and see how everyone is doing. And let me double check the chat really quickly. Okay. Um, so I asked, what else is it? Yeah, so there's a lot of other applications. I think this is the easiest way to understand it. But we'll talk about like more applications going forward. But I want to introduce the concept like this. But yeah, I think this is good for like, well, actually, no, I won't spoil it because it's really interesting. Yes, I'm not going to say anything. Um, Bhavit, yes, Bhavit, that's a good summary. Yeah. Okay, so the thing you're dividing by, that's 12, right? We'll say 12 is the modulo. So we're taking like this entire thing modulo 12. And when we say modulo 12, everything, we're just dividing everything by 12. And so in this case, like 15 divided by 12 has a remainder of 3. That's correct. So what we say is because 15 and 3 have the same remainder when divided by this like modulo 12, we'll say that they're congruent. Okay? Does that notation make sense to everyone? Awesome. Hitharth understands it. Oshrit says, so mod is remainders. Yes, Oshrit, that's correct. Vic says, I'm kind of stuck in the remainder. Everything else is fine. Okay, no worries. So the big idea here is like, okay, let's say we're dealing with 15 over 12, and we'll do it like long division. But I guess it's not really long division. Like this is pretty short, right? So obviously like 15 or 12 goes into 15 one time. And like obviously you have a remainder of 3, right? So like 15 is equal to like 1 remainder 3 remainder. And let's say like now you divide 3 by 12. So like 12 doesn't go into 3 like any times. Like it's not possible to divide 3 by 12 because 3 is less than 12. So we'll say like it goes into 12 goes into 3 0 times. And so if you subtract that 0, you're left with a remainder of 3 again. So because these remainders are the exact same, 15 and 3 have the same remainder when divided by 12, that means we'll say they're congruent modulo 12. So you can think of like modulo as like divided by. Okay. And congruent is like basically equals, and this is basically like the remainder. Okay. All right, so that I think that's like a good translation of like everything on the screen. So like in reality, this is not like new content. Like you guys know what remainders are, you guys know what divisors are. You guys like know how to find out like what like you know how to find a remainder. So all this stuff is like not new like concepts. We're just putting a cooler term to it. We're putting a fancy term, and it'll allow us to do like a lot of nice work. But yeah, Ashrith, I see you have your hand raised.
This looks complex when you put like mod in brackets, but like basically all it is the remainder. Like there's nothing else
Yes.
to it.
Yes, that's correct. So the reason why we write it like this, it's because you'll probably encounter like more complex problems where this notation is like actually needed. But for right now, like this seems to get a lot in the way, right? But I promise you, like there's a reason why we use this like kind of writing. So yeah, this kind of like the expression here. If this equation is confusing, please let me know because like I will be using this notation a lot and I won't be explaining it very in depth going forward. So I just want to make sure like we're all clear on how this looks. Um, but okay, I see a lot of yeses. So I think we're doing okay. Um, okay, awesome. Okay. Wow. So I'm just scrolling through this chat and I see like a lot of like spam and stuff. And I was trying to look for questions, so that kind of like I wasn't able to find a lot of stuff. So like if we can maybe cut the spam so I can see if like there's questions because I think this is like unfamiliar to some people. So let's just make sure we're keeping this like the chat open and stuff. I leave it open so you guys can like ask questions and answer questions because I think like sometimes that helps a lot more than me answering. But I guess if that's getting like misused and like like we're not talking about math. I'll go ahead and cut it off. I know I say this every class, which makes me kind of sad that I have to say it every class. But I will actually cut it off at some point if it gets to be distracting. Okay. Okay, so let's go ahead and keep talking. Let's see. All right, here's our next question. I just want to make sure we are all on the same page. Um, all right. So consider this like statement, which I have just made bigger so you guys can actually read it. So 23 is congruent to 8 mod 5. Is this a true or false statement? Go ahead and put that in the chat, whether you think it's true or false, and we'll go ahead and talk. Okay, Samhit says false, Ashrit says false, Hitarth says false, Adi says true, Anvika says true, Sia says true, Nahal says true, Anvika says true, Jason says false, Sai says true. Bhavit says false, I assume. Sai says true. Okay, I feel like we're like kind of split. I want to say there's more people saying true. Okay, okay, I think more people are saying it's true. Okay, so let's break this down. Um, okay, first of all, modulo 5, right? That means we're dividing by 5. That's an important part. So remember, we want to see, do 23 and 8 have the same remainder when divided by 5? Well, okay, if I divide 23 by 5, I'm getting something that looks like 4, remainder 5. Is this familiar to everyone? Like, does everyone like get that this is 4 remainder 5? Or is this new? I don't know. Like, I feel like this is how I wrote it when I learned it. Okay, cool, cool, cool. Good. Sometimes like notation changes and it gets like confusing. Yeah, R5 is like remainder because I don't want to write it. Well, yeah, I feel like this is how it's always been. Yeah, yeah, yeah. Okay, amazing. And then 8 divided by 5, it's obviously like 1, remainder 3. Oh, oops. Now I see what you guys are saying. I put R5 instead of R3. Sorry. Thanks, guys. Okay, cool. So you have remainder 3 in both cases. And because their remainders are the same, this is actually a true statement. So this is true. Okay, that's correct. Now I think for the people that are saying it's false, I think where this is a little confusing is the fact that this is 8, which is greater than 5, right? And like 23 divided by 5 does not have a remainder of 8. But what's important to remember is what the congruency sign represents, right? This congruent sign means like their remainders are equal. So remainders are equal, okay? So it doesn't matter if the numbers themselves are equal. Otherwise, we would just use like some kind of equal sign, right? But because we're dealing with congruency, we want to show that these numbers have the same remainder when divided by the modulo, or 5. And so because of that, we checked our work here. We can see that both remainders are 3, so they are congruent modulo 5. Okay? Think about like congruency in triangles, right? Congruent triangles are the exact same triangles. It's the same thing here, except they are congruent in terms of remainders. Okay? Awesome. Let me take a look at the chat super quick. Yeah, oopsies. Yeah. Sorry guys. I see all your messages about R3. Yes, that's my bad. Sometimes I like say one thing and then I write another. It's definitely like disconnect somehow. Um, okay, awesome. Okay, great. Let's go ahead and okay, so I'm glad we're on the same page here. So that's kind of like how modular arithmetic works, kind of how the remainder stuff works. Okay, this might seem boring. This is like, Sam, why is this your favorite topic? That's because you can do a lot of cool stuff with remainders, stuff that is not necessarily obvious at first, but you can prove a lot of really cool things. I will also say like modular arithmetic probably appears on every major math competition. Typically, number theory is underrepresented in competition problems because like it doesn't get interesting unless it's very like complex stuff. So you'll see a lot more like algebra, geometry, counting problems, and then like maybe 5 number theory problems, which is sad. But that's okay. So out of those number theory problems, I'd say a good bit of those tend to come from modular arithmetic because it's something that's pretty easy to understand, and it's something that most people are familiar with. They just don't know what the terms are. So that's kind of what we'll be talking about, but this stuff like relates to like divisibility, prime numbers, some really cool theorems. And if you're like maybe looking into applications in math, or maybe you're like a computer science kid who likes math, this stuff is like super, super important in encryption algorithms. So I guess like if maybe that's something you guys are interested in. That is definitely something like number theory is useful for encryption. So I would definitely check that out. But yeah, okay. I see some questions. Sia asked, does this help with number sense and spread on math? Like, absolutely, yes. This definitely comes up in number sense. There are a lot of problems using modular arithmetic in number sense. Maybe you don't realize it just yet, but it's definitely there. I remember using some of these techniques for sprint as well, but I don't know if that's changed since I did math like literally a decade ago. But yeah, okay. Um, okay. So let's talk about some quick properties and then hopefully we can start applying them. So to start off, if we have, and I'll rush through I'll go through this pretty quickly because I think they're intuitive for most people. Let's say we're dealing with two different congruences. Um, A is congruent to B mod M, and C is congruent to D mod M. One important thing, note that these are both mod M, meaning they are both like the same modulo, okay? So we have four different rules. We have the addition, subtraction, multiplication, and powers rule. I'm sure you guys can guess already what these mean. The addition rule basically just says that like A plus C is congruent to B plus D mod M. That makes a lot of sense. Same with subtraction. A minus C is congruent to B minus D. I'm not really going to write that. Multiplication, I think, is a little more interesting. It's A times C is congruent to B times D mod M. Notice it's not M squared. It's just mod M still, which I think is interesting. And then also like A to the power of N is congruent to B to the power of N mod M. Okay, I think this one is probably the most powerful rule, and it's something like this is probably the most common application you will see of modular arithmetic. So like definitely keep this in mind. Important, I will write. Oh, that arrow is pointing to no equation. Okay, this is important. Yeah, okay. Let me look at questions. All right. Samhith says, when I heard of modulo, I thought of Python modulo operator. And Samhith, that is a perfect connection to make because modulo in Python and modulo in math are the exact same things. If you've ever used the modulo operator there, you're doing the exact same thing we're doing here. So yeah, we call the mod modulo. So it's the same thing. Yeah. Oh, Atharv asked, what does mod m mean? Mod means modulo. So mod m means modulo m. And this is basically like divided by. So modulo is basically like divided by m. Okay, so we're saying like a is congruent to b divided by m. That's literally how the equation translates, or how that statement translates into words. Cool. Alex says I don't understand the power one. No worries, we will go over that. Um, awesome. Okay. Sai, I think I saw your hand raise. Sorry, I didn't let you unmute before because I was answering some stuff. But if you want to ask your question, go ahead.
Uh, I don't understand like the third property. What is it called?
This part?
Yeah.
Oh, it's the power rule. Yes. And we'll go a little more in detail on this because I think this one's more like harder to understand. Okay, awesome. Before we talk about this a little more, let me see if anyone else has questions. Okay, Advik also asked to go a little more in depth on that. Awesome. And Ashraf as well. Okay, yes, so let's go into this. Okay, so this one is like probably the most important rule, I would say. And the reason why is like if you guys have ever seen these questions with like, what is the last digit of 12 to the power of 89? And you're like, how am I supposed to do 12 to the power of 89? That's what this rule is for, okay? So let me Okay, Asha says, where did you get n from? So n is like any random power. So no matter what power you raise a and b to, this like congruence will always be the same. Um, so Asha says use the last digit and find, yeah. Okay, Asha, that pattern or that method you're talking about is inspired by modular arithmetic. Yes. Okay, awesome. And that's actually one of the problems we're gonna do. But yeah, I won't spoil it any further. So if you guys have no idea what I'm talking about, like, don't worry. Okay, so this power rule is basically saying like, if I take an example, let's say I have 3 to the power of 5. Um, well, okay, first of all, I have 3 is congruent to 1 mod 2. I think this is like, everyone can agree with this. Like, this is pretty easy to see. So if I have 3 to the power 5 is congruent to 1 to the power 5 mod 2. This is a good example. I think it's a simple example, but it's a good example to show that if you're raising both of these powers to this, or if you're raising both of these numbers to the same power, and you continue dividing by the same value, it's gonna end up being the exact same congruence. Like the congruence is gonna stay the same. And the reason why that is because like these are both the same remainders, right? So obviously if you raise it to the same power, the remainder when you divide by the number is gonna be the same regardless. So I think that's like the big rule here. Okay, cool. I think I'm gonna go ahead and close the chat now because I think there's a lot of like other stuff going on. But yeah, okay. Yeah, let me stop sharing. Okay, cool. Okay. All right. So this is modular arithmetic. Or well, this is the power rule. So if that makes sense, well, okay, if that doesn't make sense, go ahead and raise your hand and we'll ask questions. But yeah, otherwise, feel free to go ahead and kind of just chill out. I'll give you guys all a moment to like process all this. But yeah. Yeah, Ashrit, go ahead.
Never mind. I was just asking you to turn on direct messages. You turn it on.
Oh yeah. So you guys can now chat with me only. Just because there was a lot of spam before. So yeah, I just wanted to clean that up a little bit. Yeah, Adi, go ahead.
You were saying how we could solve like the 12 to the power of 89, like the last digit problem with that. Can you show us how to do that?
Yes, absolutely. And that's actually something we'll cover today. So we will totally get to that. No worries at all.
Thank
But yeah, glad you want to hear about that. Yeah, that I think a lot of people know the method for that. But the method is actually rooted in modular arithmetic. So understanding like where that comes from will be super duper helpful. Okay. But yes, we will totally talk about that today. Okay. So, oh, yikes, I don't know what I just did. Let's go ahead and make this smaller. Okay, so those are the main rules. I would say the power rule is probably the most important one, but I think maybe the product rule is good to know. And actually, let's go ahead and test the product rule just because like this is like somewhat important. Yeah. Okay, so go ahead and find 47 times 53 mod 10. What is this value? Okay, starting to see my answers. So Sai says 1, Janish says 1 as well. Bobbit says 1, Nahal says 1, Tommy says 1. Amazing. Okay, I think I see a lot of answers. Someone says 1, and he's trusting his mental math, so I think he actually did this in his head, which is crazy cool. Athar says 1, and Vika says 1. Amazing. Okay, so let's go ahead and kind of talk about this. I think, yeah. Jason also says 1, Advik says 1. Amazing. Okay, cool, cool, cool. Wow, so many answers. Okay, so let's go ahead and take a look. In this case, remember, refer to the product rule, right? So if I do 47 mod 10, we can say like 47 mod 10 is like congruent to um, 7 mod 10. And basically all I'm saying here is 47 and 10, or 47 and 7 have the same remainder when divided by 10, which I think like most of you guys will agree with, right? Like actually all of you guys should agree with that. And by the same reasoning, like 53 mod 10 is congruent to 3 mod 10. Okay, so now if we go back to our product rule, the product of these two is going to be the same as the product of 7 and 3 mod 10. So I could say 47 times 53 is congruent to 7 times 3 mod 10. But I know 7 times 3 is 21, and so 21 mod 10 is equal to 1, or is congruent to 1 mod 10. Okay, so this is actually just 1 mod 10. If I keep saying equals to instead of congruous, I apologize. Please forgive me. Sometimes it's just like a train of thought, but I hope if it's ever confusing, like let me know and I'll try to clarify. Okay, so another way this question actually could have been written was find the last digit of 47 times 53. And I think this is all a problem you guys have seen before, like some kind of last digit problem. This is like one of the main ways modular arithmetic helps out in math. So I think like it'll definitely be super duper relevant. But yeah, if you had been asked like find last digit of 47 times 53, you would do this like, entire process as well, okay? And you would find the last digit is 1, right? So the question is like, why do we do mod 10? Because your last digit is going to be like when you write it like in terms of place values, your last digit is the only one that is not going to be divisible by 10, right? So if I had like a number like 600, actually 47 times 53 is let's see, like 491, right? Okay, 491, I think. Maybe oh wait, no, I think I'm wrong. It should be 241. There we go. Okay. Anyway, so if you had like written this out, this would be like 200 plus 40 plus 1. That 1 in the units digit is in the units digit for a reason, right? It's because it's going to be less than 10. And so when we want to find the last digit, we'll just take mod 10 because everything else in the number will be divisible by 10 except for that last digit. So that's why like if you want to find the last digit, you'll take mod 10 and kind of like do the multiplication like this. Audie, go ahead.
Uh, to find the last digit, can't you just multiply the ones digits of both of them together?
Yeah, that's actually right. And so that's actually what we're doing here if you look, right? Because 7 and 3, those are the ones digits. This mod 10 is kind of like the rigorous way to show it, but like you can see like 7 and 3 are the units digits. That's what mod 10 shows. So if you want to go ahead and multiply that, you'll get 1. So this is like what modular arithmetic does. And I think this goes to show like you guys are already like really good at finding this last digit, doing a lot of this unit digit work. What we're doing now is explaining like why is all of this true? So I think like hopefully this is a useful lesson. But Audie, good question, good observation. You are 100% correct. Atharv has sent a really nice visual in the chat. Atharv, thank you for sending that explanation. I think that was super duper awesome of you. Okay, let me see if there's any questions. Okay, I think Sia had a question answered as I was talking. Advik asks, is tens congruent to the ones place? Yes. So taking mod 10 will show you the ones place. So I guess like maybe a follow-up question. What modulus do you have to take to find the last 2 digits? Yeah, so my question was like, what modulus do you have to take to get to the last 2 digits? So for the last digit here, we took mod 10. So what do you have to do to find last 2 digits? Okay, I see an answer from Sumhiv, which is 9. Audie says mod 100. Let's see, I think Advika says 10. Sai says 100. Sai A, I think says 100. Yes. No, maybe so. Yes, 100. Yes, yes, yes. Okay. Babit says 100. Ashrit says 100. Awesome. And yeah, okay, yeah. So I would agree with all of you guys. Yes, I would say 100. So to kind of like recap, if you have Okay, so if you're trying to find the last two digits, you would need to take mod 100 of your number. And that's because like the last two digits are obviously going to be less than 100. So if you divide it by 100, you'll find that they're the remainder. The remainder is always going to be less than 100, which is going to be represented by those last two digits. Okay, so that's kind of how that works. Ashra, go ahead, ask your question.
In usual scenarios, mod 100 makes sense, but like I'm saying, in only this scenario, doesn't mod 1 work as well?
Mod 1? Well, mod 1 is the remainder when you divide by 1, right?
Yeah.
So there's no like remainder necessarily. So that doesn't
So,
make like so you wouldn't be able to actually do anything. Yeah. Mod 1 is like I don't think mod 1 really exists because all those remainders would just be 0, right? Because everything is divisible by 1.
okay.
Yeah. Okay, awesome. But I do see what you're saying, because like 47 and 53 are less than 100, right? So like taking mod 100 would be kind of like silly. At that point, you would just multiply it out. But to like some extent, if you're working with really big numbers, then this makes sense. So actually in this case, some of you might be saying the last two digits are 21. That would actually not be correct, because 21 is assuming you're working with like mod 10, right? The last two digits, I think we showed this up here, is actually going to be 41. And the only way you can find this is just by multiplying because 47 and 53 are less than 100. So there's really not any like sneaky trick there. You just got to multiply it. But yeah, that's kind of how that works. Okay, let me see if there's any questions. Yes, so to find the last two digits, you would have to take mod 100. Okay, awesome. Okay, sorry, I'm just checking all the answers and see. Okay, Adharv has a question. How do you get 100? Because, okay, 24. Okay, let's take a look. Okay, so Adharv is asking, where does the 100 come from? Okay, so think about it this way, right? Let's kind of look at the place value of things. So if I have like a random number, I'm going to make up a random number, and we are just going to work with that. But first, I needed some more space on my screen. So let's say I have like the number like 59461. Okay, if I talk about this in terms of place values, I can write it as 5 times. Wait, actually, I'm gonna remove one digit because this is like kind of big. We'll get rid of that one. Okay, so this is just gonna be 5 times 1,000 plus 9 times 100 plus 4 times 10 plus 6 times 1. Okay, this is just place value. Like all of these are powers of 10. All we're doing here is place value, which you guys are good with. Like I know this is something you know. So what we're doing in terms of like mod 10 and mod 100 is we're dividing all of this, like this entire number. Let's say we're doing mod 10. We're gonna divide it by 10, right? So if we divide this by 10, think about the rules you learned for fractions, right? We can break this up into 4 different fractions. We can do 5,000 by 10, 900 by 10, plus 40 by 10, plus 6 over 10, right? So obviously, like these first 3 terms are going to be divisible by 10. They're all multiplied by some like power of 10. But this last term over here, that unit digit is 6 times 1. So because there's no factor of 10, like your remainder is just going to be that 6. But everything else gets divided easily. You just have this last term left over, right? So now let's say I had 100. If I had 100, my first 2 terms would get canceled out because those are both like factors of 100, or those are both like multiples of 100. But these last 2 terms are going to be less than 100 because they only have that factor of 10. They don't have a factor of 100. And so these 2 terms together will be my remainder. So 40 plus 6, or 46 is going to be my remainder in this case. And like that makes sense over here too. So like ultimately that's what we're doing over here. So to find the last 2 digits for anything, you want to divide by 100. And this is a good example to show like why that works. Okay? Awesome. So hopefully that answered questions. Hopefully that makes a little more sense. If not, feel free to like raise your hand and like ask where you are a little lost. Okay. Adi asks, so you just have to multiply it out if it's less than 100. Yes. So if your remainders are less than 100, unfortunately, you do have to multiply out the number to figure out like what it is. Okay, I think everyone is doing better now, which is good. This is good to see. Okay, so let's go ahead and talk about some more problems. I think this next section is like what you guys are really looking forward to, finding powers and stuff. Ashra, I did see your comment before about maybe asking to explain a problem. Yes, you can definitely explain. I think this is something similar to like what you would like to explain. Yeah. Okay, awesome. So, like I said before, one of probably the most powerful techniques for modular arithmetic is finding patterns modulo m. If for power is a modulo m, right? So I guess like probably, oh, what did I just do? I have no idea what I did. Okay, probably one of the most like popular questions you guys have seen is something like that looks a little bit like this. I made up a random question with 12 to the power of 89. We'll go and stick with this next example for now. But yeah, you guys have probably seen a question like, what is the last digit of 7 to the power of 100? So if you guys know, go ahead and answer. I'm going to go ahead and open back up the chat because I think we will all benefit from talking to each other. But let's make sure we're using it the right way, okay? So go ahead. What do you guys think the last digit of 7 to the power of 100 is? If you know. It's okay if you don't. We will talk about how to figure it out. I'll just ask if 3-digit times 3-digit is supposed to be okay, yes. I replied to your question separately because I think that is easier. Okay, awesome. So I see answers from a lot of people. Okay, someone says I can never solve these, which is totally okay. We will learn how to solve them today. Oh, okay. So I see a lot of people raising their hands, which makes me think you guys cannot chat with each other. So let me fix that. Yeah, as soon as I said that, I see all hands go down. Okay. Well, I think I have to like stop sharing for this and then go here and then yes. Okay, now you guys can chat. Stellar. Okay, cool. All right, so I see a lot of people saying one. Audie says pattern. Samhit says one question mark. Bhavit says one. Ashrit says one. Sia says a pattern with 7931, and the answer is one. Bhavit says one. Amazing, because the last digit pattern. Okay, stellar. This is good. Okay, this is really good. So yeah, I would agree with all of you guys. The last digit answer is one. Ahmed, right now we are looking at the last digit of 7 to the power of 100. But yeah, if you missed anything, feel free to go check out our recording after class. Okay, so I think a lot of you guys are talking about this last digit pattern. I think Ashrith had a solution before about this. Ashrith, if you want to explain, you can go ahead and talk about like what is this last digit pattern?
So what I learned is to find this, there's always a pattern in when you do like use exponents. For example, let's say 2 to the power of 1, 2, then last digits would be 4, 8, 8, 6, and then that repeats over and over again. So you can do the same thing with 7. If we take the first 5 powers, or last digit, it gives us 7, 9, 3, 1, and then 7 again, which tells us it's repeating.
Yeah.
And then since the cycle is 4 terms long,
Mhm.
if we count 100 every time, like skip counting by 1, the 100th one would be 1, 7 to the power 4. So, yeah.
Yeah, awesome. Okay, so there are many, many ways modular arithmetic comes out here. But it's so intuitive for you guys that you don't really even think about it. But first of all, thank you, Ashrith, for explaining that solution. I think it was very well said, and very well explained. And I think a lot of other people had arrived to the answer in a similar way. Okay, so I want to talk about like the primarily modular arithmetic way, and then we'll return to this solution and talk about like where the modular arithmetic kind of pops up. Okay. So let me scoot this over to the side for now. Or I would say like probably the coolest way I would suggest doing this is kind of again looking for a pattern, right? So we want to find the last digit, which means we want to take mod 10. Think about our discussion of place values before, right? So if I have 7 to the power of 1, this is just congruent to 7 mod 10. Nothing really interesting here. But if I take 7 squared, this is going to be congruent to 9 mod 10. And you can kind of see this by multiplying the 7 by 7 again, right? And you'll get 9. And if I have 7 cubed, mod 10. That's going to be 9 times 7, or 63. So that's going to end with a 3 mod 10. And then if I have 7 to the power 4, this is going to be 3 times 7, or 21 mod 10, which is basically just 1 mod 10. And this looks basically like this thing over here. So like these are the same things. I'm just writing out that extra step in between about that mod 10, right? Because that's like what you guys are doing with the maybe this notation, like kind of gone. So now, because the pattern repeats every 4 powers, we can say like 7 to the power 4 raised to the 25th power is congruent to 1 to the power of 25. Think back to that power rule I mentioned before, right? I said that was super duper duper important. That's where this is coming into play, right? So let me like annotate this maybe. Wait, I feel like I've used all my cool colors. Okay, I'll do orange, I guess. Power rule. This is good. I feel like every field in math has its like very cool power rule. Power rule is always cool. Okay, I'm just rambling because you guys probably don't understand what I mean by that, but that's okay. Okay, so mod, oh my gosh, wait, I thought I switched to purple. Purple, there we go, mod 10. Okay, and so this is like super cool. Like this is easy to see. This is just congruent to 1, right? So what I've done is I've made Oshra, your solution is correct. There is nothing wrong with it at all. What I've done is I've made it a little more rigorous. And the reason why I want you guys to start thinking in this way, or like maybe adopt kind of this mindset, is because you will start encountering problems that are not just like one line or what is the last digit, right? You'll start getting more crazy stuff like what is the last digit of 2 to the power of 500 minus 3 to the power of 296 or something crazy like this. And now all of a sudden, like maybe that pattern stuff kind of starts to fall apart, right? And so the pattern stuff will hold for some time, but then when you start getting into like maybe you're looking at the last 2 digits, or maybe you're looking at some kind of sum or some like division or some manipulation of the numbers here, the pattern stuff starts becoming a little more complex. So in this case, like modular arithmetic is probably like a more rigorous way of looking at things. Okay. Okay, I do see a question, so okay, never mind. The question has been answered by something that I said, which is great. Okay, Anvika, I see your solution as well. Thank you so much for sending that. That is absolutely correct. Um, cool. All right, I see a question from Sai A. So let's go ahead and talk. But before I do that, I just want to make sure there's no other questions. Okay, cool. Yes, you guys have been doing modular arithmetic this entire time and never realized it. But it's important now that you realize it because you can solve a lot more harder problems now that you know it. Okay, stellar. So let's go ahead and like recap the process here so that way we can all be on the same page. What we're doing is basically we're taking Oshrin's solution, which I think a lot of you guys know, and we're just adding that modular arithmetic element to it, right? So the reason why Oshrin's solution works is because he's actually doing like modular arithmetic this entire time. He's just not necessarily writing it in the notation, right? So if we take the number 7, 7 mod 10 is just going to be 7, right? It's going to be congruent to 7. Nothing special here. Once again, the reason why we're doing mod 10 is because we're looking at the last digit. Remember, the last digit we can find by taking a modulus of 10, okay? So this is where this first part comes from. Then, if we go ahead and look at 7 squared, remember, that's just 7 to the power of 1 times 7. So if I multiply this by 7, I'll get 49. And so 49 is just congruent to 9 mod 10. And I guess you can write that like intermediate step kind of in here. So 49 is congruent to 9 mod 10. Okay, that's kind of the step here. And then when we get to 7 cubed, we're going to actually take this 9 instead of 49 and multiply it by 7. And so when you do that, you will get something that looks like 63. Okay, and then you kind of do the same thing here. You'll do 7 times 3 to get to 7 to the power of 4, and that'll be 21. Okay, so notice how like this goes here, and you're multiplying by 7. And so once you establish this pattern, you kind of just raise this congruence to 25. This will come out to be 7 to the power of 100, and that's congruent to 1, because 1 to the power of 25 is just 1. Okay? So that's how this all works out. If you have questions, let me know. Otherwise, we'll go ahead and check out another question. Okay. see, I want to maybe do like another question. Okay, yes. Let's do, okay, here's a good question that's not mod 10 and is actually challenging because maybe you guys will get away with figuring out this like mod 10 stuff. Okay. Oh, yeah, I see some questions. Sorry, I just saw that. Um, oh, sorry, I just missed it. There's something, okay. Um, okay, Asha, that's how did you get 63 and 21? Basically what I did was I took I took the modulo of 9, or I took the remainder 9, and I just multiplied it by 7. Instead of finding what 7 cubed is, I'm taking the remainder by 10 and just multiplying it again by 7, because that's how I get from 7 squared to 7 cubed, right? I have to multiply by 7. So I'm just doing the product rule, except I've abbreviated it a lot because I didn't want to write out all of that. Yeah. Thank you, Sumhith and Audie, for putting that in the chat as well. That's a good explanation. Okay, fire. So let's go ahead and do one last question. And this is actually a math counts question. I think I would say this is probably like maybe chapter round. Yeah, I would say this is a chapter round question. But yeah, what is the remainder when 2 to the power 50 is divided by 7? So I think a little bit more challenging than our previous mod 10 stuff. Okay, I see an answer from Oshrith and Hitharth and Vika, awesome, and Janesh and Samhith and Amith and wow, okay, so many people that I just cannot say everyone's names. And Nahal and Jason, I think. Yeah, okay, awesome. So let's go ahead and take a look. Cool. So we're gonna kind of do the same process as before. Starting off, we have 2 to the power of 1 is obviously congruent to 2 mod 7. Nothing crazy here. Because like I just have 2. 2 is less than 7, so nothing crazy. All right. 2 squared is congruent to 4 mod 7. Okay. All I'm doing here is just multiplying both sides by 2. That'll get me to 2 squared here and 4 here. 4 is still less than 7, so I'm not doing any simplifications. And then I get to 2 cubed. So 2 cubed is equal to 4 times 2, which is 8, which is actually congruent to 1 mod 7. Okay, this is super duper nice. So if I take 2 cubed, oopsies, I don't know what happened to my pen there. So I have this 2 cubed, right? I need to get as close to 50 as possible. So I'm going to do 2 cubed to the power of 16. That only gets me to 2 to the power of 48. This is close enough, but not entirely. So to get to 2 to the power of 50, I need to do 2 cubed to the power of 16 times 2 squared. Okay, so this is a little bit of like product rule, power rule mashup stuff. But if we go ahead and kind of take care of this, we'll get 1 to the power of 16 times 4. Okay, and so 1 to the power of 16 is just 1 times 4, so that's congruent to 4 mod 7. Okay. So I think it was initially tricky because it wasn't just mod 10. This actually worked out really nice, right? Because 8 mod 7 is just 1. This is like super nice. But yeah, okay, so another good example of this, I made this look easy. Well, I'm glad this looked easy because this is just stuff you guys have seen before, so don't overthink it. I just want to like add some I guess add some of the more like technical stuff because now that you like know this modular stuff, you can do some cooler problems. Actually, when I attended the governor's honors program like 2 years ago, I did a research project on like modular arithmetic because it was super cool. But yeah, okay, so we'll go ahead and do some like challenging problems next week. I think I'll try to find some more like I guess some more like competition style challenging problems where it's not just like find the pattern and you're done. We'll find some more complex stuff. But yeah, okay. Let me see if there's any like pressing questions. Challenge. Unfortunately, it is 9 o'clock, so no more problems for today. The homework should be like a good review. Maybe there'll be a couple challenge problems in there. But next week, like we'll do some good problems, and you guys will really see why I love modular arithmetic. But yeah. Okay, thank you all so much for joining me. I will see you all next week. I hope you learned something new, but if you have any questions, or you have like anything at all, please feel free to reach out. Okay? All right, thanks everyone. Bye. Have a great weekend. I will see you all next week. Yeah. Yeah, Sai, go ahead.
Where did we find the homework?
The homework should be emailed to you. Yeah, the homework should be emailed to you after class. So like after every class, we'll send you an email with homework handouts and whatnot.
Thank you. Bye.
Of course. Yeah. Ashraf, go ahead.
My question was, so basically what I did for this, tell me if it's right. I quickly did this. I used a pattern rule, but instead after each one I got, I did mod 7 after that like you did.
Mhm.
But then I got the cycle of 3, so I did 50 divided by 3,
Yes.
and I got remainder 2. So I
Yes.
just did the second one in the pattern. Would that work?
Yes. Yes, that's good. The reason why sometimes I caution against that is because you won't always have like a nice example where the remainder happens to be one. Sometimes you'll get an example where it's just like the remainder is always like three or something or five. And in that case, it's a little bit harder figure out like to figure out what the value is because you have to do the process multiple times. Does that kind of make sense?
Yeah.
Okay, so today like we did more of the easier problems where you could still get away with like looking at the just the remainders or the cycles. But I think at some point it you kind of have to start using modular arithmetic just because like it's hard. You can't just like raise to the power of one. Okay,
Okay. Yeah.
awesome. But yeah, your solution is absolutely right. Like that's correct.
Okay. Bye.
Okay, awesome. Bye, Ashra. Yeah, Advik, go ahead.
Um, so I still have a question on this problem.
Yes.
Like what I did was like 2 to the power 1 up to 2 to the power 5 because like it repeated like 2 to the power 1 is 2, right? And then 2 to the power 5 ends with a 2. So like now I don't like really know what to do after.
Yeah. So you can look at the cycle of five, but I will say like if you go power by power, you'll see quickly like you already get a power of one, right? At mod 7. And like getting that remainder of one is really nice because anything you raise to the power like anytime like one is raised to any power, that's just one, right? So that's why like we don't really go past 2 cubed because 2 like or because this is enough. Actually once you look at 2 to the power of 4, you'll see that the remainder um ends up being 2 again. So this in this case, it's actually a cycle of 3. It shouldn't be a cycle of 5 for mod 7. Okay?
Okay.
Does that
And
make so the cycle of 5 thing, or I guess the cycle of 4 is what you're probably referring to. That only is true for like powers of 10. Otherwise, I think it's not necessarily, it doesn't always work.
and
Yeah.
also why do you do 4 over here, like all the way at the bottom, like 1 to the power 16 times 4?
Oh, that's because if we just did 2 cubed to the power of 16,
Yeah.
that only gives us 2 to the power of 48.
Oh yeah,
But we
no.
need to get to 2 to the power of 50. So that's
Yeah.
where this 2 squared comes from.
Okay,
And
now.
that's 4. Yeah.
Yeah, okay.
Okay.
Bye.
Awesome. Bye, Althvik.
Bye.
Alrighty, I'm gonna go ahead and close the Zoom room, but thank you all so much for joining me and have a great evening. Bye, everyone.